Assalamualaikum warahmatullahi wabarakatuh. In this time, I would like to present my paper with the title Sustainable Energy Storage Management for Power Plants, Transmission Station System with the Hybrid Power Generations and Stochastic Electricity Production. The paper is a part of our dissertations in Institute of November. The first, I would like to present the background of our research. In recent years, the research dealing with the electrical energy storage has received a great deal of attention from scholars and practitioners. Wakhid et al. 2015 developed a method to determine the optimal energy and power storage capacities in electrical energy storage system, or EESS, by using a kinetic algorithm. The objective of the model is to minimize the total operational cost of microgrid change. Nyoman et al. 2019 studied the influence of EES utility on the total cost and energy saving by considering some aspects, such as energy quantity, energy price, and characteristics of the systems. Furthermore, some scholars developed the EESS by using an inventory approach. Schneider et al. 2016 employed a Muse Finder model to formulate EESS on apartment equipped with a photovoltaic system. Recently, EESS has been extended by some authors to an electrical supply chain problem. They propose a new model known as electrical energy supply chain system, which is developed using joint economic resizing problem approach. They argue that the process of determining the optimal energy storage is similar with the process of specifying optimal load size energy output. Wakhid and V 2018 proposed the EESCS consists of power plant, transmission station, distribution station, and customer with the stochastic electricity demand. And then Wakhid et al. 2018 also investigated the influence of price-dependent demand on energy resizing decisions. Various types of demand are investigated to show how it can influence the behavior of EESCS. Our review shows that the problem concerning with emission reduction and the employment of cleaner power generations were readily discussed in the literature. So here we propose a new model of ICIMECE, or Sustainable Electrical Energy Supply Chain System, consisting of two parties. The first is the power plant, which has two power generations and the transmission stations. The electricity demand from a customer in a transmission station is normally distributed, which means D and the standard deviation alpha. The transmission station use a continuous review policy to manage the electrical and historic level. The green power generation in a power plant is cleaner than the regular power generations, hence it emits a lower emission. The electricity production cost of the regular power generation is relatively cheaper than that of the green power generations. We assume that the two power generation here work in parallel to generate electricity production. And here we propose alpha as a decision variable, where the alpha is the allocation factor for the electricity production in two power generations. And we assume here the supply rate of power generation is restricted by the maximum supply rate. And here we have some notation in transmission station and also some notation in power generations. We have average of the electrical demand as T, and tau is for a standard deviation of the electrical demands, and some notation also for the power generation. For example, K1 is the setup cost for green power generation, and K2 is the setup cost for the regular power generation, and P1 and P2 is the power supply rate for clean power generation and also for regular power generation. And also in a power plant we have some notation related to the emissions parameter. A1, P1, and C1 is the emission parameter for clean production, clean power generations, and A2, P2, and C2 is the emission parameter for regular power generation. And also we have some parameter for electricity production. G11 and G21 is the emission, the production cost parameter for clean power generation, and K12 and K22 is the parameter for the production cost for regular. And here we have four different variables, where N is the electricity power distribution factor, and Q is electricity power consumption, and K emergency breaker factor, and alpha is the allocation of the electricity production. And here the mathematical model of our proposed model. The transmission cost consists of the transmission cost, ordering cost, storage cost, and breaker cost. And the cost for the power plant consists of two total costs. The first is for the green power generation, and the second is the cost for regular power generation, where each total cost consists of setup cost, storage cost, carbon cost, and the production cost. And by conducting the differentiations, or by we can see we can find the optimal value of K and the optimal value of Q. And here we propose a new algorithm to solve the problem by adopting the iterative procedure from Pendaya and Harika 2004. We have 11 steps to solve the proposed problem. And this is the result. Figure 1 is the figure for the impact of the change in production cost parameter on power supply rate and the demand satisfied by power generations. We can see from the figure 1 that if the green power generation electricity production costs increase, the system tends to allocate more production to the regular one. It seems that the electricity demand satisfied by the regular power generation significantly increased, while the electricity demand satisfied by the green power generation decreased. This phenomena is intuitively correct, since moving from the expensive production cost to cheaper production cost will consequently reduce the total cost. And then figure 2 shows the impact of the change of the production cost parameter on the carbon emission and total cost. We can see that if a power generation electricity production cost increased by 400%, the emission released by the regular power generation and clean power generation changed by 8.37% and minus 4.7%. In addition, the total cost incurred by the regular power generation and the clean power generation increased. We noted by giving the flexibility to the decision maker to allocate the electricity production, the system can maintain the power supply rates, which lead to reducing the total cost. And figure 2 here show about the investigation of the impact of the change in emission parameter on power supply rate and the demand satisfied by power generation. We can see from figure 3 that if a regular power emission parameter increased by 40%, the electricity demand satisfied by the clean power generation and regular power generation changed by 6.35% and minus 10.81%. Further, the regular emission parameter change also gives the similar impact on the power supply rate of the power generations. Figure 4 for the investigation of the impact of the change in emission parameter on the emission and total cost. We can see from figure 4 that the amount of emission generated from the clean power generation and total cost incurred by clean power generations increased to the increase of emission level of the regular power generation. It can be understood since moving from the production from the regular power generation to green power generation will consequently increase the power supply rate and electricity generated by green power generations. And this is the conclusion and future research direction. As the final section of this paper, to comply with the carbon tax regulation implemented by the regulator, the power plant can manage the emission by controlling the allocation of electricity production. However, this action to control the emission is not easy because it confronts with the electricity production costs. And second, the model gives the guidance for a decision maker to manage electricity storage in EESCS. The research showed that allocating the electricity production wisely and controlling the power supply rate, the emission released from power plant, and joint total cost can be minimized simultaneously. And then the model can be developed further by considering the inclusion of electrical energy loss and the setup cost reduction. And this is the end of our presentation. Thank you for joining the presentations. Assalamualaikum warahmatullahi wabarakatuh.